Welcome back to another video. So today we'll be going through the 2021 HSC physics paper. So this paper has 100 marks worth of questions and you've got 3 hours to complete that with 5 minutes of reading time. So just make sure in that reading time, go through, check out the entire exam, identify if there's going to be any trouble problems for you. So that way you know to allow a little bit of extra time for those problems when it comes to it. And if you do finish reading through the entire exam in that reading time, then I recommend going back and start working out some of the multiple choice problems. With that being said, let's get into it. So, question 1. A marble is rolled off a horizontal bench and onto the floor. So, rolling the marble at a slower speed would, okay, so we've got a few different options. Increase the range, decrease the range, increase the time of flight, decrease the time of flight. So we know it's not going to be either C or D, certainly not, because that has nothing to do with the horizontal velocity. That is all strictly going to be based on variables like the height, the vertical velocity, and the gravitational acceleration. So definitely not C or D. And we know that if I roll it faster, well, it's going to go further, right? So clearly rolling it slower would just mean that it would drop off and hit the floor a little bit quicker. So we'd say that that would decrease the range. Okay, so now moving on to part 2. So a positively charged particle is moving at velocity v in an electric field as shown. So what is the direction of the force acting on the particle due to the electric field? So keep in mind this is an electric field, not a magnetic field. So we know that with an electric field, a positive particle will always move in the direction that the electric field points. So in this problem here, we see that the electric field points up the page, and so that's going to be our answer. So part C, up the page. All right, question 3. Which of the following is not a fundamental particle in the standard model of matter? So an electron, gluon, muon, or protons. So if you remember your standard model, then you can identify the answer is going to be proton. But the other way that you can kind of get there by elimination is just by thinking about, well, is there anything smaller that makes up an electron or a gluon or a muon? Not really. But for a proton, we know that it is made up of quarks. So we know where quarks are on the standard model, so we can kind of exclude protons then. Okay, now moving on to question 4. So an astronaut is traveling towards Earth in a spaceship at 0.8 the speed of light. At regular intervals, a radio pulse is sent from the spaceship to an observer on Earth. Which quantity would the astronaut and the observer measure to be the same? So we have the length of the spaceship, the speed of the radio pulses, the momentum of the astronaut, and the time interval between the radio pulses. Well, we know that relativity will tell us very clearly that the perceived length, the momentum, the time interval, so the time dilation, those will all change. But one of the postulates states that the speed of light remains constant no matter what reference frame you are in. So what we can say then is that the speed of the radio pulses will remain the same. Since, of course, radio pulses are just a component of the electromagnetic radiation spectrum, which is always moving at the speed of light. So, part 5 now. The spectrum of an object is shown. So we have our intensity and wavelength graph here. So which row of the table correctly identifies the most likely source of the spectrum and the features labeled Y? Okay, so we've got a couple different options. So star or discharge tube, and is it an absorption line or emission lines? So what we should recognize first of all is the general sort of shape of this graph, right? Looking a little bit something like this, we should recognize that immediately as our blackbody radiation curve. So that's going to be representing a star. So we know now it's going to either be between A or C. And now we start looking at these lines here that Y is indicating. So do those look like emission lines or absorption lines? Well, hopefully we recognize those as absorption lines for this particular diagram, since we can see that they are sharp decreases in the overall intensity of this graph here, which should otherwise be a fairly smooth function. So star, absorption lines, and there we go. So our answer for question 5 is going to be A. Now, moving on to question 6. So the diagram shows part of a nuclear fusion process that occurs in stars. So it then asks us, what is the isotope labeled R? So right at the end, what is this? Okay, so we know that that's a proton and that's a neutron. So this has 2 protons and 1 neutron. So let's have a quick think about our periodic table. So 2 protons means it's the second element. So we know our second element is helium. So now we know it's not A and it's not C. And now what is the atomic mass of this going to be? Well, it's going to be 3 because we have 2 protons and 1 neutron. So there we go. So now for question 6, D will be our answer there. All right, moving on to question 7. In a certain ideal transformer, the current in the secondary coil is 4 times as large as the current in the primary coil. Which row of the table correctly identifies the type of transformer and the ratio of turns? Okay, so what I recommend we do here is have a quick look at our equations for transformers. So we know that we can write it out as V primary over V secondary is equal to N primary over N secondary. That's going to be one equation we know we can use. What's something else we know we can use? We can use the voltage primary times the current primary is going to be equal to voltage secondary, current secondary. Okay, and so coming from this second equation over here, I might be tempted to rewrite this as Vp over Vs is equal to Is over Ip. Okay, so what we can do now is we can use that Vp on Vs and simply replace that with Is over Ip and substitute that back into this expression over here. And so now what we should have is Is, so the current secondary over the current primary is equal to the number of turns in the primary over the number of turns in the secondary. Okay, and so now we have that. Let's quickly reread that question. So it says the current in the secondary coil is 4 times as large as the current in the primary coil. So what that means is essentially that Is over Ip is just going to be equal to 4. And so if Is over Ip is going to be equal to 4, then that means that the number of turns over the number of turns in the secondary coil is also going to be equal to 4. So that means now that this must be in a ratio of 4 to 1. So now looking at this, it says ratio of turns in primary coil to turns in secondary coil. So it's now 4 to 1. So fantastic, we know that. So now it's either going to be A or C. So is it step up or step down? Well, let's have a quick look at this. So the current in the secondary coil is 4 times as large. So now if we look at this expression right up the top here, so we've increased the secondary current. What does that mean for the secondary voltage, however? That means we must decrease the secondary voltage. And so if it is going down in that voltage, then that means it's going to be step down. So now we know that it's step down and it's in a ratio of 4 to 1. So our answer here is going to be 7C. Okay, now moving on to part 8. So, light from a point source is incident upon a circular metal disc, forming a shadow on a screen as shown. A bright spot is observed in the center of the shadow. So there's our little setup there on that apparatus. So the bright spot is caused by a combination of, so what do we reckon? Interference and refraction, refraction and polarization, polarization and diffraction, or diffraction and interference. So to get this question correct, we just need to know essentially what these terms actually mean. So interference is the superpositioning of these waves, so whether they will add, so it means you can add maybe 2 waves look like this, and then the resultant wave would be something like that. So that's going to be what interference can cause. Refraction, well, that's the bending of light through an object when it enters a different medium. So it's not really entering a different medium here, so we know it's not going to be refraction. Polarization, well, that's just essentially looking at the direction that the light is oscillating. So we know that doesn't really have too much to do with it in this particular situation. So we know it's not going to be polarization. Now, diffraction. Okay, diffraction is literally just the bending of light around an object. So the way I always like to imagine this was, imagine you're laying in your room at night and you've left your door open just a little bit of a gap in your door. And it's all dark in your room except there's a light on out in the hallway outside your room. And what happens? You would expect maybe there would just be a sliver of light going into your room like this, but what you actually see happening is that yes, there is that sliver of light and it's very, very clear, but the rest of your room also lights up. And the reason for that is because of diffraction. So it's the bending of light around corners. So with that being said, we know that for this particular case, there will definitely be diffraction going on. And now we just need to determine whether this is going to be due to diffraction and polarization or diffraction and interference. So given the fact that they've told us it's a bright spot occurring at that point in time, we should probably recognize that there's most likely going to be referencing the interference. And so that means that our answer for question 8 will be D. Okay, now moving on to question 9. So a mass M is positioned at an equal distance from two identical stars as shown. The mass is then moved to position X. So which graph best represents the gravitational potential energy, U, of the mass during this movement? Okay, so we've got a few different options here, but some of these make a little bit more sense than others. So for example, we should probably recognize that D immediately makes very little sense, so we can get rid of that very, very quickly. We can also probably have a look and see that A also isn't going to be a very good indicator of what would be going on there, since we know that it's going to be changing its displacement between these two stars here. So just looking at the right star for a quick example, we know that initially it's going to be further away than as opposed to when it's right in the middle, it's going to be closer. And then as it gets further away again, that will be the exact same distance as that point there. So we know that it's not going to be A because it won't stay constant. Now, it's either between B or C. But let's have a quick think about what I've just shown here. We've said that initially it's at a further distance than halfway through. So the further you are away from a star, the greater your potential energy will be, respectively. So we know that it's not going to be B because that shows an increase in potential energy. And so what we should see is that it's going to be answer C, since as we get closer to the star, the potential energy will decrease and the kinetic energy would increase. And then after the halfway point, when we start going away from the star, the potential energy increases and the kinetic energy would also decrease there. So answer here is going to be C. Now, question 10. So a strong magnet is moved past a copper block at a constant speed, as shown. So what is the direction of the force acting on the copper block? Okay, so for this question, we need to be comfortable with Lenz's law, Faraday's law, and all that sort of stuff, and then we can get a bit more of an intuitive understanding as to what exactly would be going on. Okay, so the direction of the force acting on the copper block. So let's have a quick look at what would happen here. So the magnet is moving to the right, and that's creating currents within that metal block. There'll be circular currents, most likely looking something like that. And we know that it's going to want to create a force to reduce these currents and to reduce the total movement of this whole system. So now, how can it do that? Would it be into the page or out of the page? Certainly not. That doesn't really make any sense, because if it came out of the page, it would hit this magnet, and if it went into the page, it would just be repelled by this magnet, and if it's just a copper block, that definitely wouldn't really happen. Okay, so now it's going to be either to the left or to the right. Now, if it moves to the left, what's going to be happening here? The velocity, or the relative velocity between the magnet and the block would be increasing, which would in turn increase the current. So that would actually create a little bit of a paradox, right? Because we'd then just be creating more and more energy from nothing. So we know that it must actually be pushed to the right. And the reason for that is due to the conservation of energy. Because if we move it to the right, then it will stay in a, relatively to that moving magnet, it will stay in a constant position, which will reduce the total electrical current induced in the surface on that copper block. So there's a lot going on in this question, but as long as you're comfortable with Lenz's law and Faraday's law and probably have seen a fair few solenoid questions, then I think you should get a decent grasp on this question. So our answer here is 10B. Okay, so what is the peak wavelength of electromagnetic radiation emitted by a person with a body temperature of 37 degrees Celsius or 310 Kelvin? Okay, so for something like this, well, we need to know law that we're going to use, and so that is Wien's law. I believe I'm pronouncing that correct, spelled W-I-E-N-S, so Wien's law. So the way that this is explained is that the peak wavelength is going to be equal to Wien's constant, which is represented with a B, over T. I'm not actually sure why it's B, but it is what it is. And we know that B is equal to 2.898 times 10 to the negative 3, and we won't worry about units here. And for T, that's going to be the temperature measured in degrees Kelvin, okay? So we know that T is equal to 310. So what we can say now is that the peak wavelength is going to be equal to 2.898 times 10 to the negative 3 over 310. And when we put that into our calculator, we get an answer of 9.3 times 10 to the negative 6. And that is part A. Okay, there we go. So moving on to question 12. Which graph shows the magnitude of back EMF induced in a DC motor rotating continuously at different angular velocities? Okay, so DC motor, and we know that it's just looking at the different angular velocities here. So the magnitude of back EMF and the angular velocity are our two different axes here. So what do we know about back EMF? Well, we can say that it is, approximate to, I'm just going to write it out like this. It's going to be proportional, I should say, to d phi over dt. So now, whereas phi is going to be measuring the angle, and so d phi dt is simply the angular velocity. So since it's proportional to this term here, that means it's going to be a linear relationship. So a linear relationship eliminates immediately options A and option C. So now we're between B and D here. Now, the one thing that we need to be really careful of here is the magnitude of back EMF. So since it's the magnitude, and because there is normally, I believe, like a negative n in here, but as I said, we're not really fussed about that, the magnitude is going to be increasing as we increase the angular velocity. The magnitude would not be decreasing. So our answer here will be D. Okay, now moving on to question 13. So the diagram shows electron transitions in a Bohr model hydrogen atom. So which transition would produce the shortest wavelength of light? Okay, so the shortest wavelength of light means that there's going to be the highest frequency. So I'll quickly write that out. So shortest wavelength equals highest frequency. And we know that the highest frequency is going to be representing the most energy in the different transition. So which one of these would represent the most energy? Well, it's pretty clearly going to be the transition X, going from the 5th energy level down to the 1st energy level. So that is the largest gap that we can jump here, and so that represents the most energy. So therefore, our answer is going to be B, X. Okay, now, question 14. Which of the following statements correctly describes the gravitational interaction between the Earth and the Moon? So, A, the Earth accelerates towards the Moon. Well, that's correct. So, honestly, we could just tick that and keep going on with our answers. But let's quickly read over the rest and see exactly what's going on now. Part B, the net force acting on the Earth is 0. Not quite true. Part C, the Moon and Earth experience equal and opposite accelerations. Again, not quite true. And part D, the force acting on the Moon is smaller than the force acting on the Earth. So, well, quickly looking at it, in fact, we don't even need to know too much about the Earth-Moon system to really explain why this is incorrect, because B, C, and D essentially all just nullify each other. So there's not much going on here since they all seem to contradict. So we know that the only one that actually stands alone by itself is part A. So if you can spot what's going on in the wording of the question here, then pretty clearly you can just pick out A as your answer. Now, part 15, unpolarized light is incident upon two consecutive polarizers as shown. The second polarizer has a fixed transmission axis which cannot be rotated. Now, I1 is the intensity of light after the first polarizer, and I2 is the intensity of light after the second polarizer. So how would I1 and I2 be affected if the transmission axis of the first polarizer was rotated? Okay, so let's see what's going on here. So we have some light going through, and then it hits our polarizer, and let's say those are our lines here. So then it comes through, and it still looks something like that. And let's say maybe I2 is somewhat at an angle, and then you would have our second I2 actually would come out after that second polarizer, I should say. So what's happening here? So if I change I1, nothing really will change with regards to the intensity of I1. So I should say if I change the angle of the first polarizer, nothing will change with regards to the intensity here. But if I now made this completely perpendicular, so if I made it completely perpendicular to the second polarizer, then you'd see that nothing would actually come out of I2. So the only thing that would definitely change here is I2, so the second intensity. Okay, so part 16. So the sun has an energy output of 3.85 times 10 to the 28 watts. By how much does the sun's mass decrease every minute? Okay, so what we need to use here is the energy mass equivalence, so E equals mc squared. So we know energy is going to be 3.85 times 10 to the 28. So watts is joules per second. So what we need to do is times that number by 60 to show it for each minute. So what we can say now is rearranging for m as well. So m is going to be equal to E over c squared. And now just quickly substituting those values in. So we'll say 3.85 times by 10 to the 28 times by 60, since it is a minute. And now divided by the speed of light squared. So we'll just say 3 times 10 to the 8 all squared. And now just quickly putting that into your calculator, well, we see that the answer is going to be B, 2.57 times 10 to the 13 kilos. Okay, now question 17. So two long parallel conductors, X and Y, are connected to a light bulb and an AC power supply. The conductors are suspended horizontally from fixed points using sensitive spring balances. X is positioned directly below Y. Okay, so which statement correctly compares the forces measured by the spring balances? So the forces measured on X and Y will always be equal, okay? The force measured on Y will be greater than or equal to that on X. The force measured on X will be greater than or equal to Y. Or there will be a continuous reversal of which measured force is greater. Now, since we know that it's AC, it's going to be very, very tempting to just immediately put D and then move on and try and save a bit of time with your exam. But that would actually be incorrect here. So what we need to do is let's quickly consider, so it is alternating, but let's consider the situation where the current is going, let's say, clockwise in this system. So that means on the top, so on the Y, it's going to the right, and on the X, it would be going to the left. Now, since these are two currents moving in the opposite direction on parallel wires, we know that the forces between them would actually be repelling. So that would push wire Y upwards, and that would push wire X downwards. So we know that if it's going clockwise, it will increase the force going down on X and decrease the force going down on Y. So now, what about if it's going anti-clockwise? Well, for Y, it would be going to the left, and for X, it would be going to the right. And so what we see is actually the exact same sort of situation. It's two currents on parallel wires going in opposite directions. So what that means now is that the force on X would increase, and the force going down on Y would decrease. So what we can say now, fairly safely, is that the force measured on X will be greater than or equal to that on Y. And there we go. And that's simply, again, just based off the fact that they're always going to be repelling each other. Okay, now, question 18. So, an evacuated chamber contains a pair of parallel plates connected to a power supply and a switch which is initially closed. So a positively charged mass falls within the chamber under the influence of gravity from the position shown. So when the mass has fallen half the height of the chamber, the switch is opened. Which of the following correctly shows the trajectory of the mass? Okay, so let's have a quick think about what's going on here. So we've got we've got two parallel charged plates here, and we see that there's a positively charged mass going to be falling through it. So initially, the switch is closed, so that means that there is a flow of electricity through this circuit here. So that means we are creating an electric field in this situation, and that electric field is going to be going this way, right? Since this directs the flow of energy clockwise here in this circuit. So initially, for halfway, it's going to be a force to the right. So we know that it would then experience a force going to the right, and also the force going downwards due to gravity. So initially and for the first half, we should say that there's just a force pushing it down essentially to the bottom right. And then halfway through, we now open up that switch, so in that way there is no longer an electric field there. So what happens now? All that's left is, in terms of acceleration, is going to be the acceleration due to gravity. And so what happens now is that there's still an initial velocity pushing it to the right, but the acceleration due to gravity will be increasing. And now it's very hard to draw this, well, I should say. But hopefully what we can see is the one that this corresponds to is pretty much A. So B is just a straight line all the way down, so that would be the situation if there's just a constant force, the entire way through. C and D are also, well, they look very, very, very similar to me. I'm struggling to find a real difference between these two. It looks like D might be a little steeper than C, but in either case, that would probably represent perhaps the case where you turn it on halfway through rather than turning it off halfway through. So our answer for this question, 18, is going to be A. Okay, now moving on to question 19. So rhodium-106 is a metallic beta-emitting radioisotope with a half-life of 30 seconds. So a sample of rhodium-106 and an electrode are placed inside an evacuated chamber. They are connected to a galvanometer and a variable DC power supply. And that's exactly what we see in our circuit diagram here. So a student measures the current I when the power supply is set to 0. They then measure the stopping voltage, V sub S. The stopping voltage is the minimum voltage needed to prevent current flowing. So a few minutes later, these measurements are repeated. So how do the two sets of measurements compare? So the trick to this question here is that the half-life is only 30 seconds. So that means after 30 seconds, there's only going to be half of the initial amount of rhodium-106 remaining. So what that means then is that the total number of electrons will be cut in half, or the total number of photo-ejected electrons is going to be cut in half, right? Since that is exactly what beta emission is. It's simply electrons given off by a radioactive substance. So if we're now reducing the number of electrons by a factor of 2, then what will happen? Will the stopping voltage change? Not quite. Will the current change? Yes. So since the number of electrons is reduced, then that means we are reducing simply the number of electrons or the amount of current, simply by definition. Now, the stopping voltage will not change since the electrons will still be emitted at the exact same, or approximately the exact same energy levels. So for question 19, our answer here is going to be A. Okay, now moving on to question 20. So a metal cylinder is located in a uniform magnetic field. The work function of the metal is phi. Photons having an energy of 2 phi strike the side of the cylinder, liberating photoelectrons which travel perpendicular to the magnetic field in a circular path. The maximum radius of the path is r. So if the photon energy is doubled, what will the maximum radius of the path become? Okay, fantastic. So what we need to work out real quick is just a few different things. So first of all, the energy of the photoelectron. So we know that E equals HF minus phi, so the work function. And HF here is the energy of the photon, so we know that's just going to be 2 phi. So 2 phi. So we know that the energy of the photoelectron initially is just going to be phi, the work function. Okay, what else do we know about this system? Well, for a photoelectron, we know that its kinetic energy will be equal to the energy given to it by the photon. So we can say half mv squared is going to be equal to phi. So that energy there. Now, what else do we know? We can quickly solve that for v, for the velocity of this electron. And what happens then is we have that the velocity of this electron is going to be given by 2 phi over m, and then square root that entire thing. Okay, so now we have the velocity. What else do we know about this whole system? Well, we know that it's moving in a circular path. So what I can say from that then is that if it's moving in a circular path, we can say it's approximating circular motion. So that means we can write out that its force is going to be equal to mv squared over r. So it's centripetal force. All right, so what we can do now is quickly solve this for r. And what else do we know? The force on this is going to also be equal to qvb. And we could say qvb sine theta, but we know that already that it's given that it's perpendicular, so we don't really need to worry about that too much. So we know that qvb is also equal to the force. And so now we have a couple of different equations here that both explore the force on this electron. So what we can do now is work these two out and solve for r. And we can say that r is going to be equal to mv squared over qvb. And well, we see that there's a v squared in the top and a v in the bottom, so we can cross those out as such. So now we have the radius is given by mv over qb. Okay, fantastic. And what exactly is v again? So v is dependent on the work function and the amount of energy given into that electron via that photon. So we can now replace that velocity here with the velocity that we had already found out earlier. And we find that the radius for the path that this electron is circling around is going to be equal to m on qb times the square root of 2 phi over m. Okay, so now the question is, if the energy is doubled, what will the maximum radius of the path become? So now by doubling the energy of the photon, well, that changes from a 2 phi into a 4 phi. And now this energy on the electron is no longer going to just be phi, it'll be 3 phi. So now we can go through and quickly change all these values just by putting that 3 out the front here. And so I'm going to write that in like that. So just 3 phi in brackets. And then down here, we see that that would change from phi into 3 phi. So now, if the photon energy is doubled, what will the maximum radius of the path become? Well, we see that the only thing that has actually changed here is that factor of 3. And so we see that the only solution here is going to be d. So the square root of 3 times by the radius, since we know that that's the only thing that has changed, whereas initially r was equal to m over qb times the square root of 2 phi m. And so you can see now very, very clearly that it's only changing by a factor of the square root of 3. And there we go. So that's the end of the multiple choice section. Now let's get started on the extended responses. So now on to question 21. A DC motor is constructed from a single loop of wire with dimensions 0.1 meter times by 0.07 meters. The magnetic field strength is 0.4 Teslas and a current of 14 amps flows through the loop. So part A asks us to calculate the magnitude of the maximum torque produced by the motor. So this is a formula that we should be familiar with. It's on our reference sheet. So the torque, tau, is equal to NIAB, and we don't need to worry about writing in the sine of theta, since we know that we're looking at our maximum, so obviously we will exclude that. Now, N is the number of turns in the loop, so we have one single loop given right there. I is the current, so we know that that is 14 amps. A is the area, so that's going to be the multiple of these two. And B is the magnetic field strength. So all we need to do now is simply substitute those values in, and we'll see what we get. So it becomes 1 times 14 times by 0.1 times by 0.07 times by 0.4. Okay, and so now writing that out and putting that into our calculator, we get 0.0392. And now let's quickly see how many significant figures should we write this to. Well, all of these are written to 2 significant figures, so now we would like to write this to the same. And so we can simply write that out as 0.04 Newton meters. And there we go. Okay, so that's part A all done. So now on to part B. Describe how the magnitude of the torque changes as the loop moves through half a rotation from the position shown. So we should be somewhat comfortable looking at this diagram and recognizing how the torque works here. So if I wanted to graph this out, I might actually say that my torque is going to be on the y-axis, and I'll simply say that our angle is going to be on the x-axis here. So what we see is that we will start from a maximum, and then we'll start heading down, and then we'll start turning back up. And then that is 1/2 rotation. So a quarter rotation takes us from a maximum down to that minimum 0 there. Then another quarter rotation takes us from that 0 point back up to the maximum over here. And then you can guess it realistically. If we wanted to continue extending that, we know that it would just be pretty much symmetric continuing on as such. However, we're only concerned in the first half turn. So now if we wanted to write that out, we could probably write that out something like this. So we can say the torque begins at a maximum and decreases to 0 at 90 degrees from the initial position. The torque then increases to a maximum again at 180 degrees from the initial position, since that would now be the entire rotation all the way to the other side. Okay, now on to question 22. So a horizontal disk rotates at a constant rate as shown. 2 points on the disk X and Y are labeled. X is twice as far away from the center of the disk as Y. So it asks us then to compare the angular and instantaneous velocities of X with those of Y. So anytime I see a question that asks us to compare something, I know that I can probably simplify things by just making up a table here. So what I might do is we'll simply write it in as X and Y. Okay, so let's quickly think about the angular velocities first of all. Well, I'm going to quickly draw that origin in there. I'll call that O. So you see that since they're both on that line from the origin extending to that part on the circumference there, well then they're actually going to have the exact same angular velocities all the way through as they are on the same disk, and they'll be rotating in the same direction. So what we can say is that angular velocity, we might just say is equal to a constant. And then for y as well, we'll say angular velocity is equal to the exact same constant. So as long as you're identifying clearly that they're both going to be equal to the exact same value, then that should be completely fine here. Okay, now let's start looking at the instantaneous velocities for both points x and y. So let's actually start with point y since it is closer to the origin here. So how do we find the instantaneous velocity? Well, we know from our study of circular motion that the velocity is going to be given as 2 pi r divided by t, the period. So we don't actually have any of the actual numbers here to then substitute this value in, but what we can say is that the velocity of point y is going to be equal to 2 pi times the radius, or the radial distance, of point y from the origin, divided by t, whatever that period may be. So now if we start looking at the instantaneous velocity for x, well, it's going to be equal to, once again, 2 pi, and I could write it as rx. However, what do I know about rx? So the distance from the origin to x, I know is twice as big as the distance from the origin to point y. So what I can do now is I can actually just write that in as 2 times ry, since I know it's twice the distance there. And that is now divided by t. So what does that tell us? Now that clearly tells us, we can say, therefore, angular velocities are equal. Vx is equal to 2 times Vy for instantaneous velocities. And we should also note, since we are observing the velocities here, that they both move in the exact same direction. And I'll just conclude that here. I'll say both in the same direction. Okay. And there we are. So that is question 22. Now on to question 23. So it asks us to describe how Millikan and Thomson each used fields to determine properties of the electron. So let's quickly familiarize ourselves with these experiments. So we know that Millikan is famous for the oil drop experiment, in which he atomized oil droplets and then was able to suspend them mid-air by balancing the forces from an electric field and the gravitational field. And for Thomson, we know that he was very, very famous for discovering the charge to mass ratio of electrons, and that was performed using electric and magnetic fields, balancing the forces on electrons. Okay, so let's get that written out in words. So the sample answer given to us on the HSC marking criteria is Thomson used electric and magnetic fields to balance forces on electrons, allowing him to calculate the charge to mass ratio of electrons. Yep. And Millikan used electric and gravitational fields to levitate charged droplets, allowing him to determine the charge on the electron. Yeah, so pretty much what you would expect for us to be putting into this answer. So just quickly identifying what these experiments actually did and proved, and then the interaction between the different and relevant fields in each experiment. Now, moving on to question 24. So, a stationary coil of 35 turns and a cross-sectional area of 0.02 meters is placed between two electromagnets and connected to a voltmeter as shown. The electromagnets produce a uniform magnetic field of 0.15 Tesla through the coil. The magnitude of the magnetic field is then reduced to zero at a constant rate over a period of 0.4 seconds. Calculate the magnitude of the EMF induced in the coil. So we know our equation here is given by EMF is going to be equal to minus n, the number of turns, d phi, the change in flux, and dt, the change in time. Okay, so let's quickly figure out, well, what is the flux here? Well, the flux, so d phi, in fact, must be equals to the change in magnetic flux across this area, and we know that that is going to simply be given as 0.15 times by 0.02, or essentially 0.003. Okay, fantastic. So that's how much it will change by, and that's how much it's decreasing, okay? So since it's starting from a positive magnetic field pressure, then it will go down to have zero magnetic field passing through, then we know that this must be a negative since it is decreasing. Okay, now for dt, so the change in time, well, it says 0.4 seconds is the entire time that this all happens across. So we can simply write that out as 0.4. Okay, and what about n, the number of turns here? So we know n is equal to 35. That's given to us right at the top here. Okay, so now plugging these numbers all into our calculator, let's see what we get. So the EMF is equal to minus 35 times by negative 0.003, now divided by 0.4. And so solving that, we see that this is going to be equal to 0.3 volts. Okay, and that's question 24. Moving on to question 25. So a satellite is launched from the surface of Mars into an orbit that keeps it directly above a position on the surface of Mars. Okay, so we know what those types of orbits are called. We know they're called geostationary orbits. So we are given that the mass of Mars is 6.39 times 10 to the 23 kilos, and the length of the Martian day is 24 hours and 40 minutes. So part A asks us to identify two energy changes as the satellite moves from the surface of Mars into orbit. Okay, so generally when we're looking at satellites, we know that we're going to be mostly worried about gravitational potential energy and kinetic energy. So let's have a quick think about how they might change as it goes from the surface of Mars now out into the orbit of Mars. We know that the height above the surface is going to increase, so therefore we can say that the gravitational potential energy must increase. So we can quickly take note of that. So gravitational potential increases. Okay, now what about our kinetic energy? Will that increase or decrease? We know that we need to increase the velocity so that way it can actually, achieve escape velocity and get out into orbit. And so if we are increasing the velocity, that obviously means that we are increasing the kinetic energy as well. So then we can therefore say kinetic energy increases. And there we are. So that is two energy changes for this satellite. Okay, now for part B, it asks us to calculate the orbital radius of the satellite. So we need to refer back to Kepler's laws. So we should know that r cubed over t squared, the period, is equal to g, the gravitational constant, m, the mass of the heavier object here, which is going to be the planet, not the satellite, divided by 4 pi squared. Okay, so quickly rearranging for r, the radius, well, we know that r must therefore equal to the cube root of, so g is 6.67 times 10 to the negative 11, times by m, the mass of Mars, which was given above as 6.39 times 10 to the 23. And then we also need to be moving that period squared up across. So what do we know about the period squared? Well, that's the number of seconds that it takes for us to go around one complete orbit. So we have it given in 24 hours and 40 minutes. So how many seconds is that? Well, that would equal out to be, so 24 times by 60 and then plus 40, that would give us 1,480. So that's how many minutes there are in a Martian day. Then we'll times that by 60 to get it into SI units, into our seconds. And then we'll simply square that as is required by this square here. And now we simply divide through by 4 pi squared. Okay, and now plugging that all into your calculator and seeing what that is equal to, we get now a radius of 2.0 times 10 to the 7 meters. And that's question 25. So now moving on to question 26. So a student performs an experiment to measure Planck's constant h using a device that emits specific frequencies of light when specific voltages are applied. So the voltage V needed to produce each frequency f is given by V equals hf over q sub e, where q sub e is the charge on an electron. So data from the experiment is shown, and that's represented in that table here. Now, part A asks us to graph this data on the axes provided and include a line of best fit. Okay, so very generous of them to already give us our axes. So we know that frequency must be on the x-axis and voltage on the y-axis. So now all we need to do is pick an appropriate sort of range for these values on these axes. And let's start with the voltage, so our y-axis first. So we know it only goes up to 2.6. We've got, let's see, 1, 2, 3, 4, 5, 6 intervals. So maybe we'll start here at 0 and go up by 0.5. I think that should work out quite nicely for us. And yep, there we go. Okay, so that's our y-axis labeled. And what about our frequency? We go from, well, 3.5 all the way up to 7. And it is, of course, times 10 to the 14. So let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8 different markers on the bottom. So maybe we'll just say 1, 2, 3, 4, 5, 6, 7, and we'll put that 8 one in there as well. Okay, so now all we need to do is graph this data. So when we have a frequency of 3.5, we have a voltage of 1.3. So 3.5, that would be right here, around here. And so that would lead us to have maybe something right around there. Okay, and now continuing on, so when we have 4.8 as our frequency, we have a voltage of 1.7. Alright, so 4.8, that would be about there. 1.7 should be, I believe, around there. And then 5.3 and 1.9, well, that one is now going to be approximately there. Maybe a little bit lower. Alright, and the last one here, frequency 7 and voltage 2.6. So that one is going to be smack right on that line there. And in fact, just on that corner there. So now all we need to do is include a line of best fit. So it does look like a pretty linear graph here. And make sure you use a ruler, but it should look something like this for your line of best fit. And that should be okay. And you can extend that a little bit. There's no stress in doing that. Okay, so that's part A, all sorted. So now part B. It says the student proposes using data point 1 to calculate a value for Planck's constant. So can we justify a better method to calculate Planck's constant from the experimental data provided? Well, to me, the first thing that I would consider is why have we done an entire experiment and collected 4 different data points if the person is only going to use one data point? So right off the bat, we should see that as something that's a bit weird and perhaps a bit unnecessary if that was their plan. So what we can say here is that it would be better to use the gradient of the line to calculate the value, as this would take into account more data, right? So counteracting that problem there. And it would also increase the accuracy by also including all that additional data. And that is the easiest way that you can get the full 3 marks for part B. Okay, now moving on to question 27. So a student is considering how to levitate a thin metal rod in a strong magnetic field of 1.2 Teslas. The current flowing through the rod will be 2.3 amps. So using a labeled diagram, show a suitable orientation of the current and the magnetic field to achieve this outcome. Include relevant forces in your diagram. Okay, so we need to have a floating thin metal rod. So what I might do first of all is quickly draw up that thin metal rod. Something like that. Okay, so now what we want to do is essentially just pick a direction for the current. Okay, and then we'll see what we can work from that. So now we'll say, let's say our current goes to the right. Okay, fantastic. So that's all we need to start with for now. And let's consider the forces on this thin metal rod. Well, I know that there's going to be some force pushing it downwards, of course, and that is the weight force, right? So there must also then be an opposite force pushing it up, which is going to be due to the magnetic field. So we'll call that F sub B. Okay, so again, just field due to the magnetic, force due to the magnetic field there. Okay, so now what we need to do is we need to consider how can I direct my magnetic field such that I would experience a force pushing this upwards. Well, we would use our right-hand palm rule, so we know that our thumb points in the direction of the current, so that would be to the right. Then we know that our palm points in the direction of the force, so now we want our palm facing upwards. So if our thumb's pointing to the right, our palm's facing upwards, that means that our fingers, representing the magnetic field, are going to be going into the page. And so that's what we would do here. We would just simply put these little crosses in to represent that that is our B field. Okay, and that is a fully labeled diagram of this experimental setup. So now moving on to part B. So explain why the maximum mass per unit length of the rod cannot exceed 0.282 kilograms per meter. Support your answer with a calculation. Okay, so probably by looking at this, you're thinking, what the hell's going on here? This is a very weird question to be thrown out at you, especially with that weird value there. But what we do know about supporting this rod in thin air is that the forces must be perfectly balanced. So what that means for us now is that mass times gravity, so the weight force, must be equal to BIL sine of theta, right? So this is just our force from the gravity and our force from the magnetic field. So what we want to do now is see how can I relate this to this value down here. So kilograms per meter. Well, it just so happens that we have one measurement of mass in here. And on the right-hand side, we have one measurement of length, which is L. So what I want to do now is ideally rearrange this so that way I have M over L. And doing that, well, let's see what we get. So M over L is going to be equal to BI sine theta over G. And now we actually know what B, I, and G are. And for sine theta, well, we'll just say that it's 90 degrees, clearly. So substituting in those values, let's see what we get. Well, our magnetic field is 1.2 Teslas. Our current is 2.3. And then times by a sine of 90. I'll write that in, although we know that's just going to be 1. And then divided by 9.8. And when we actually put that into our calculator, well, we see that that is the 0.282 kilograms per meter. And that's exactly what we see, and that is our answer to part B. Okay, so now moving on to question 28. So a spaceship travels to a distant star at a constant speed v. When it arrives, 15 years have passed on Earth, but 9.4 years have passed for an astronaut on the spaceship. So what is the distance to the star as measured by an observer on Earth? So seemingly a bit of a random question there at the end, but we know how to approach this problem. So the first thing we recognize is that we're working with time and special relativity. So we'll write down our formula. So t equals t naught over root 1 minus v squared on c squared. And so we know that t naught is going to be the time experienced by the person moving at relativistic speeds. So now what we can do is, well, we'll quickly write that down. So t naught equals 9.4, and we know t by itself is going to be equal to 15. So what we want to do now is rearrange and solve for v, because that will tell us the velocity of the spaceship, and then we can figure out from the velocity and the time taken exactly how far away this star is going to be. Okay, so what we want to do here is multiply the denominator up to the other side and then divide both sides by t. And so what we'll be left with is root 1 minus v squared on c squared is equal to t naught over t. Now squaring both sides, we get 1 minus v squared on c squared equals t naught on t all squared. Okay, and then at this stage, it probably shouldn't be too difficult to rearrange for our velocity. So simply subtract 1 from both sides, or maybe you would add v squared on c squared to both sides and then subtract the right-hand side. In any case, we'll go through it. We'll go through it. So then it will become 1 minus t naught on t, and that is, of course, all squared. Then multiply everything by c squared, and then and then take the square root. So we can say that v is going to be equal to square root of c squared times by 1 minus, and then in additional brackets now, t naught on t all squared, close bracket. And so when we do that, we find that v has a value of about 0.779 c, so 0.779 the speed of light. Okay, and so now going back to the original question with that velocity, so it says what is the distance to the star as measured by an observer on Earth? Okay, so measured by the person on Earth, so that means we're going to be using the time experienced by the person on Earth. So S equals ut, our very typical displacement formula. So that's now going to be equal to u is velocity and t is time taken. So 0.779 c times by 15 years equals to 12 light years. And for this, it's okay to leave it in years here, because then we know that we'll just end up with a measurement of light years. Alternatively, you can write this out in SI units. There's absolutely no problem with that. It makes it a little bit of an additional, algebra for you. All right, and that's part A. So 12 light years. So now on to part B. It says, outline how special relativity imposes a limitation on the maximum velocity of the spaceship. So what we know about special relativity is that we have a few different equations that kind of dictate the momentum, the time, and the length of the object undergoing relativistic motion. So when we actually examine the momentum equation, well, what we realize is that the relativistic momentum approaches infinity as the velocity approaches the speed of light. So what that actually means then is that you'd need an infinite force to accelerate it faster than the speed of light, and that is actually what limits the velocity. So this is the little sample that I've written up earlier here, and that would tick all the boxes and get you the full 2 marks for this problem here. Okay, so that's question 28. So now moving on to question 29. It's rather a fun one here. So Bohr, de Broglie, and Schrödinger each proposed a model for the structure of the atom. So how does the nature of the electron proposed in each of the 3 models differ? So I really enjoy this question. The main reason that I do is because it's actually a fantastic opportunity for us to just use a table. So by setting it out like this, where we can clearly identify the scientist, the name of the model, and then the nature of the electron in that model, it makes it really, really easy for us to actually write this out. But it also makes it extremely easy for the marker in the HSC to just go through and be like, all right, yep, tick, 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 full marks, because at the end of the day, a happy marker is a generous marker, okay? So by setting it out very, very nicely like this, it will help us in the long run. All right, so let's quickly look at all these in any case. So for Bohr's planetary model, we see that the electrons are represented as just negatively charged particles that orbit the nucleus at discrete energy levels. For de Broglie, going further in time now, electrons act as both a particle and wave, and they exist in standing waves about the nucleus. And then lastly, coming to Schrödinger over here. So this is using the quantum mechanical model where we're considering electrons as waves that will model using the Schrödinger equation. Okay, so that's pretty much it. That's how you would achieve five marks for a question like this. As long as you understand roughly what each scientist and their proposed model actually means, then there's no reason that you shouldn't be able to achieve full marks on this question. Okay, so now on to question 30. In an experiment, a proton accelerates from rest between parallel charged plates. The spacing of the plates is 12 centimeters, and the proton is initially positioned at an equal distance from both plates as shown. And we are to ignore the effect of gravity here. So for part A, it says the electrical potential energy of the proton is recorded in the following graph for the first 5 centimeters of its motion. So on the same graph, sketch the corresponding kinetic energy of the proton over the same distance. Okay, well, we are ignoring gravity, so we know that we're only going to be observing the relationship between electrical potential energy and kinetic energy here. So what we need to identify now is obviously that there is a conservation of energy. And so how many units of energy do we start with when we are purely electrical potential? Well, we have 1, 2, 3, 4 units of electrical potential. So that means we'll start with 0 kinetic, obviously, since we know that it's starting from rest. But now, again, conservation of energy. So how high up will this line go? How high up will this line go that represents the kinetic energy? Well, since the electric potential energy drops to a unit of 1 energy, then we know it still must be conserved and go all the way up to 4. So that means it'll be 4 minus 1. So that means now that our kinetic energy will rise up to be 3 units of energy there. So all we need to do now is just quickly connect those 2 points with that straight line there. And that's your kinetic energy. So you can quickly describe that as just KE, if you will. Okay, fantastic. So that's part A, all sorted there. So now for part B, it says the experiment is repeated using an electron in the place of the proton. So now explain how the motion of the electron would differ from that of the proton. So really quick, what we need to identify is the similarities and differences between protons and electrons. So the most glaringly obvious one is that they're opposite charges. So that means the proton would move in one direction, the electron would move in the other. So apart from that, there is one big difference as well, and that is going to be the mass, right? So we need to remember that the mass of the electron is very, very, very small in comparison to that of a proton. So what I've written up earlier here, I'll just quickly copy paste that, is that an electron would experience a force in the opposite direction since it has the opposite charge, and an electron would experience a much higher acceleration due to it having a much smaller mass. And that's actually all you need to write to be able to tick all the boxes in the marking rubric to get the full 3 marks for that question there. Okay, and that concludes question 30. Okay, so now on to question 31. So 2 identical solenoids are mounted on carts as shown. So each solenoid is connected to a galvanometer, and the solenoid on cart 1 is also connected to an open switch and a battery. So the total mass of cart 1 is twice that of cart 2. So the question now asks us to explain what would be observed when the switch on cart 1 is closed. So in your answer, refer to the current in each galvanometer and the initial movement of the carts. So the first thing that we should be able to point out is that as soon as we close that switch, we're going to see a current, okay? So we're going to see a constant direct current going through that first galvanometer, G1. And so what that'll do is it will then create a current passing through this solenoid, and we know that a current through a solenoid will create magnetic poles on either side of that. So that would induce a south pole here. Then that south pole would create a magnetic flux in cart 2. That magnetic flux would then create an EMF. The EMF would act to oppose the magnetic flux, which would then create another south pole over here. So you would see then from that EMF a brief spike in the galvanometer, on G2, the galvanometer 2. So then as soon as you've created and induced a south pole over here, you'd see that both carts will repel each other. And since cart 1 has twice the mass of cart 2, well then due to the conservation of momentum, you would see that it would have half the initial velocity of cart 2. Now I have written that all out and put that in a bit more plain English, so that way we can kind of, collect that idea and work with that. So let's see what we've got here. So I've written it down in a few different steps. So step 1, we observe that the switch is closed and a constant direct current is observed on G1. Okay, that's the first thing we notice. This current creates a magnetic field in the solenoid with a south pole towards cart 2. So that's the first thing I've drawn on there now. That left-hand side with the, left-hand cart having the south pole induced at that end there. So now, the second step of observations. We'll say that the creation of the magnetic field creates a flux in the second solenoid, and this induces an EMF which will act to oppose the change in flux according to Lenz's law. And it is actually pretty important that we do mention Lenz's law here. This creates a south pole facing cart 1. So G2 can be observed to have a brief deflection. So that's everything that we've already stated. So that means the south pole induced here, and G2 will temporarily, it would look like, let's say that's our little reading, our screen to read this off of. The ticker would go briefly to the right until it's in that position there, and then it would go back to being as it was right in the middle. Okay, for the third step of observations here, we would say that the equal and opposite repulsion of the south poles will repel the carts, pushing them away from each other. However, due to cart 1 being twice the mass of cart 2, it is half the initial velocity of cart 2, since momentum must be conserved. So that's pretty much everything we have stated whilst looking at this system of the two solenoids on the two carts, but written out perhaps a little bit more succinctly. And so this is what you would expect to gain full marks for this particular question, as this will go through and tick all the different boxes that the HSC markers are looking for. Okay, so this is a 7-mark question, so on the actual HSC you have an entire page to actually write this all up, and this is the essentials that you would need to write to get full marks. So that's question 31. So now, moving on to question 32. So 2 students perform an investigation with a piece of elastic laid out straight on a table. The elastic is fixed at one end and has 3 markings at regular intervals. The distances from each marking to the fixed end, D1, D2, and D3, are measured as shown. So there's our different markings, and that's the differences in the distances there. So a student pulls the elastic to extend it, and the new values of D1, D2, and D3 are measured. The student observes that each value has doubled. So how well do the observations from this investigation model the evidence that led to Hubble's discovery of the expansion of the universe? And we need to justify our answer. Okay, so when it asks us how well do the observations from any sort of investigation or model, how well do they model something, right? So then we're always going to be looking at the benefits and then the drawbacks of it, right? So what are the limitations of this sort of model? So now, in justifying our answer, let's have a quick look at how we would explain this. So I've already written out our answer here. So, as the elastic stretches, the marks move by a distance proportional to its distance from the fixed end. This successfully models Hubble's observation that more distant galaxies move farther away from Earth at greater speeds proportional to their distance from Earth. And that is exactly what we expect to see. So, key here is that we've said that it successfully models Hubble's observation. Now, I have included the limitation here because we should always aim to try and include some limitations when we look to discuss a model. So I've said here that the experiment is limited, however, as it only portrays one-dimensional expansion, whereas Hubble's experiment observed expansion in 3 dimensions. Now, it might be a very, very obvious sort of limitation, but it is a limitation nonetheless that we should still make sure that we state. And that's all you actually need to write for question 32 in order to get full marks there. Okay, moving on. Question 33. This is a massive one, so a massive 9-marker here. So 2 experiments are performed with identical light sources having a wavelength of 400 nanometers. Okay, so we'll quickly underline that. So 400 nanometers. So in experiment A, the light is incident on a pair of narrow slits 5.0 times 10 to the negative 5 meters apart, producing a pattern on a screen located 3 meters behind the slits. So in experiment B, the light is incident on different metal samples inside an evacuated tube as shown. The kinetic energy of any emitted photoelectrons can be measured. So that's exactly what we see going on the right-hand side here. That's experiment B. And we see the different work functions of the two metals, so nickel and calcium, and we see that photoelectrons are only observed from calcium. So the actual question here asks us, how do the results from experiment A and experiment B support two different models of light? So in your answer, include a quantitative analysis of each experiment. So that part there is really, really important. So quantitative analysis. So that means we actually will need to do some maths here, whereas the previous two questions were mostly just looking at what will happen more qualitatively. Okay, so let's start looking at experiment A. So what is experiment A? Well, clearly that's just Young's double slit experiment. So we know pretty well what happens there. And so what we can say is that in experiment A, there will be a series of bright and dark spots observed on the screen, and the spacing can be calculated as follows. So this is the quantitative part of this question. So we know that we have the formula from our reference sheet. D sine theta equals m lambda. So our distance is the distance between the two slits, which was given as 5.0 times 10 to the negative 5. So we'll put that in. Sine of theta, we don't know theta. M, we're just going to be assuming that this is going to be 1, since we'll just look for the principal displacement from the initial brightest point. So that would be looking like this distance here. That's all we're really focused on here. And lambda, well, that's the wavelength of the actual light, and we know that that is 400 nanometers. So we can say that that is going to be 400 times by 10 to the negative 9. Okay, so now quickly solving for theta, so dividing through by that constant there and taking the inverse sign, we find that theta is going to be equal to about 0.46 degrees. So very, very, very small angle there. Okay, so what else do we know about experiment A? We know that it is, there's a distance of 3 meters between the screen and the slits themselves. So what that means now is that I can actually draw up this experiment a little bit better. So let's say this is perhaps this is our primary fringe. So that's the most bright spot there. Then this is going to be our second fringe there, so our second most bright spot. So what we might want to say here is that this distance here from the slits to the actual screen itself is going to be 3 meters. We know that this angle is 0.46 degrees. And we just want to figure out, well, what is this length here from primary to secondary? Well, let's quickly call that perhaps length y. So what we can use now is we can use the fact that tan of theta is equal to the opposite over adjacent. And so what that gives us now is that to figure out the opposite here, well, we simply multiply both sides by the adjacent. And so we find that y, this distance here, is going to be equal to 3 times by tan of 0.46. Okay, and that's pretty much all we need to do for the quantitative aspect of this, and obviously we should write this out in the actual units, so it's going to be 0.024 meters. Okay, so now after we've shown that, we can then continue our discussion on what this actually means and what model this supports. So, we can now say that this supports the wave model of light, where waves from the slits interfere constructively to create bright spots and interfere destructively to create dark spots. This is actually, that's all you need to do in order to discuss and analyze experiment A, both qualitatively and quantitatively, and that is showing how it supports the wave model of light. So now if we start looking at experiment B, so what type of experiment is this? This is just the photo emission of electrons, or photoelectrons. So what do we know about this? Well, we know that in experiment B, we see the photo ejection of electrons from calcium, but not from nickel. So we can use the particle model of light to calculate the energy of an individual photon. And well, we know that that energy is always going to be given by E equals hf, right? So h is Planck's constant, f is our frequency, and we know that the frequency of light is going to be given by the speed of light divided by the wavelength. So now if I wanted to figure out the actual energy associated with one photon with the wavelength of 400 nanometers, all I need to do is just fill this in. So then I'll have the energy is equal to 6.626 times 10 to the negative 34. Now times by c over lambda, so it's going to be 3 times 10 to the 8 divided through by 400 times by 10 to the negative 9. And that will give us a value of about 4.97 times 10 to the negative 19 joules. And there we go. So that's the energy associated with one photon. And so that's why we see that the photon will only emit an electron from calcium and not from nickel, since it is greater than the calcium work function, but is not greater than the nickel work function. Okay, so what can we say now? Well, let's write that a little bit more succinctly. So we can say, since the energy of the photon is higher than the work function of calcium, but not nickel, that explains why a photon can eject from only calcium, supporting the particle model of light. And by using the particle model of light, we can calculate the kinetic energy of the photoelectrons emitted. Okay, so how do we go and do that? Well, we know that that formula is given as the kinetic energy is equal to HF minus phi, our work function. And so generously here, they've given us our work function measured in joules. So all we need to do now is actually just rewrite this out. So HF, we know that's the energy of the photon. So that's 4.97 times 10 to the negative 19. Then minus the work function, which is 4.60 times 10 to the negative 19. And that gets us a final answer of 3.70 times 10 to the negative 20 joules. And that's it. So now what have we done? We have explained how experiment A represents the constructive and destructive interference of light as waves. And then we've also shown mathematically the distance between those peaks, so the difference between the interference peaks, and so that's then supporting the wave model of light. And then on the other hand, we've also then had a look at experiment B, so looking at the photo ejection of electrons. So then we've also analyzed not just the actual energy of the photons itself that are incident on this metal, but we've then also described the kinetic energy of the actual electrons that are then emitted. So we've gone above and beyond there to even figure out the kinetic energy. And as soon as we've included all of that, then that's pretty much, that's our answer. We're done. There's nothing further that we can really analyze or discuss about these two experiments in how they support the two different models of light. So that's question 33. That is 9 marks. That is quite a hefty question, but that's all we need to do. So now on to question 34. So 7 marker now. So a 3.0 kilogram mass is launched from the edge of a cliff, and that's what we see in this diagram here. So the kinetic energy of the mass is graphed from the moment it is launched until it hits the ground at x. So the kinetic energy of the mass is provided for times t0, t1, and t2. And so that's what we see given in this table over here. Okay, so part A asks us to account for the relative values of kinetic energy at t0, t1, and t2. So it does say relative, but that does not mean we're going to be referencing anything in relativity. Okay, so just throwing that out there real quick so that way we are aware of that. All it's actually asking us to do is just discuss what's going on at T0, T1, and T2. So at T0, you could say that it is initially launched with some kinetic energy, so 864 joules. Then all the way up to T1, it is decelerating, so the gravitational potential energy is increasing as the kinetic decreases. And then as it falls back from T1 down to T2, you would say that the gravitational potential energy is transformed into kinetic energy, and hence it increases up until it hits the ground at point X. So once again, I've got the worded solution to this actually written out over here. And this one is actually just the marking criteria, like the guidelines. This is the recommended answer. The only reason I've actually copied this one word for word is because this is actually a very confusing question if you try and just word this on your own. So using their answer, it says, after the mass is launched at T0, downwards gravitational acceleration reduces the vertical velocity of the mass until it is 0 at time T1. So yep, that's pretty much what we've said already. So the kinetic energy is a minimum here, but it is not zero since the horizontal component of its velocity is unaffected by gravity. And that's why we see on our kinetic energy graph, it doesn't hit zero, it still remains a constant here. So after T1, the kinetic energy of the mass increases again as the vertical component of motion increases under the influence of gravity until it strikes the ground at T2. So the kinetic energy at T2 is greater than the values at T0 as the mass has lower gravitational potential energy than at T0. Okay, and that all does make sense. It is a very heavily worded problem and there's a lot going on here. So that's why I did want to also include the actual HSC suggested answer here. So have a think about that, pause if you need to, reread over that and make sure it makes sense. But for now, we'll move on to part B. So a little bit more of a mathematical problem now. So it says the horizontal component of the velocity of the mass during its flight is 13.76 meters per second. So then asks us to calculate the time of flight of the mass. Okay, so that's our initial horizontal velocity. And we know that it's going to be the initial and it will remain the same the entire way throughout the entire problem, since gravity only affects the vertical velocity. So what I might say is I might just say Vix, so the initial x velocity, is equal to 13.76 meters per second. So let's see what other information we know about this whole setup. So first of all, we also know that the mass is 3 kilograms. And we also know the energy at each different point here. So let's have a quick think about that. So we'll say mass equals 3 kilos, or 3.0 if I want to keep it to two significant figures. So what do we know? We've got velocity, we've got mass, and we've got kinetic energy. Okay, so what we can start looking at now is, well, what's the kinetic energy associated with the initial y velocity? So this is getting a little bit tricky here, but we know that since it starts with an initial velocity of 864 joules, and then it will decrease until it gets down to 284, then we can actually work out that the initial y velocity has essentially a kinetic energy corresponding to that difference in that table there. So to write that out a little bit more clearly, we know that since kinetic energy is given by half mv squared, we know that we can solve this for v. So doing that, let's see. So v equals, so it would be 2 times the kinetic energy over the mass, and then take the square root of that. There we are. But what is the kinetic energy difference, or what is the kinetic energy rather, of the y component? Well, that's just going to be the difference in the two measured values, since we just need to remove the purely horizontal kinetic energy from it. So that would end up becoming here 864 minus 284. Okay, and so now knowing that m is equal to 3 kilograms, we get that it's equal to now the square root of 2 on 3 times by 864 minus 284. And so calculating that, we get an initial velocity of 19.664 meters per second. Okay, and just again to quickly reiterate how I've gotten this value for our kinetic energy is, since I know that at T1, that only has horizontal velocity, right? So this is all horizontal velocity and all horizontal energy. So what that means is that it's always had a baseline of 284 joules in its velocity, and that is always going to be in the horizontal component. So now if I want to figure out the initial y velocity, well, then I need to make sure that I look at the total energy here, but I also need to subtract that 284 from that value there. And that's why we're now looking at the difference in those two values here. Okay, so now going back to one of our most typical equations. So we know that S equal, or maybe we'll rewrite it a little bit better. So V sub F is equal to V sub I minus 9.8 t. So the final velocity is equal to the initial velocity minus 9.8 t. So I'm just looking at T0 to T1 here. So the final vertical velocity, so at T1, is actually just equal to 0, right? Since that's when it is at its maximum point, so the vertical velocity is equal to 0 at that point, T1. So then I can write that it's going to be equal to 19.664, so the initial y velocity, minus 9.8t. And now solving this, we get that t is going to be given, and maybe I'll write this as t 0 to 1, is going to be equal to 2.007 seconds. Okay, so that's t from 0 to 1. So now we're going to do pretty much the exact same equation, but now we're going to be looking at the transition from t1 to t2. Okay, so again, this will follow the exact same equation, so I might just separate this and partition that over there. So let's have a quick look at what that looks like now. So v is now going to be equal to the square root of 2 over 3. Now it's going to be times by the difference here is going to be from 1,393 minus, again, 284. So this will tell us our our y velocity finally as it hits the ground. So what that means for us now is that it's going to be 27.191. That's what that will come out to be equal to. And so then we know that the final velocity is 27.191. We know that the initial velocity is 0, since it starts from the peak. So we can then write out in this same equation over here, Vf equals Vi minus 9.8t. And we know that since this is heading downwards, we can rewrite that as negative. So then it would become minus 27.191 is equal to 0 minus 9.8t. Now divide both sides by minus 9.8, and we get our value of t is going to be equal to, and again I'll write this as 1 to 2, is going to be equal to 2.775. So now we've got the time it takes for this mass to go from t0 to t1, and then from t1 to t2. So simply adding both of those together, we can say that the total time is going to be equal to 4.78 seconds. And that is our final answer for question 34B. So a lot goes into that question there, but the actual way that this is presented in solutions on the HSC working out is actually very, very different, and I think they've taken a lot of extra steps unnecessarily. So this is actually a bit of a simplified version. Perhaps it is a little bit trickier to follow than what they've gone through, but if you can understand this, then you'll be at a fantastic place going into your exam. Okay, now on to question 35. So a spacecraft is powered by a radioisotope generator. So Pu-238, so I believe that's polonium, or might be plutonium rather, in the generator undergoes alpha decay, releasing energy. So the decay is shown with the mass of each species in atomic mass units U. So we know that our atomic mass goes from 238.0495 to 234.0409 plus 4.0026. So we need to show that the energy released by one decay is 9 times 10 to the negative 13 joules. So we know that we're always going to be looking at the difference in mass here. So the difference in mass is going to be given as the initial minus the final. So that will become 238.0495. Now, what's the final? It's 234.0409 plus 4.0026. Okay, and so that gives us a value of about 0.006 atomic mass units, so U. Okay, so now if I want to convert this from atomic mass units into SI kilograms, then all we need to do is times that by this constant here, and then we'll be able to say that delta M, the change in mass, is equal to 0.006. So this is the constant here, times by 1.601, 661 I should say, times by 10 to the negative 27 equals to 9.966 times 10 to the negative 30 kilograms. Okay, so a very, very, very small mass here. Now, using our energy mass equivalence, so E equals mc squared, we can then figure out the exact amount of energy that is released here. And so as you might guess, after calculating this, so 9.966 times 10 to the negative 30 times by the speed of light squared, which we'll just write as 3 times 10 to the 8 all squared. That gives us a value of 9.0 times 10 to the negative 13 joules. And that is exactly what was required in part A. And that's all there is to it. So now on to part B, the very, very final question on the 2021 HSC Physics exam. We finally made it. So it says, at launch, the generator contains 9.0 times 10 to the 24 atoms of Pu-238. The half-life is 87.7 years. So we need to calculate the total energy produced by the generator during the first 10 years after launch. Okay, so let's have a quick think about the equations that we know. So we know that lambda is equal to ln of 2 over t sub 1/2. So lambda is our decay constant, and t sub 1/2 is our half-life, and the natural log of 2 is just a number. What else do we know? We know that n sub t, so the number of particles left after t time has passed, is going to be equal to n naught, so the initial amount, times by e to the power of minus lambda t. Okay, so let's have a quick think about what we know. So we know that the half-life, so t sub 1/2, is equal to 87.7. We know that t, so the total time passed, is 10 years. And since these are both measured in years, we don't really need to worry about converting them to SI units, since we know that they will end up just cancelling each other out here. So what else do we know? We also know n sub naught is equal to 9.0 times 10 to the 24. Okay, so now I think with all of that information, we can actually figure out, well, what's the number of particles remaining after 10 years? So we can say n sub 10 is going to be equal to n sub naught, so 9.0 times 10 to the 24, times by e to the power of, so minus lambda t. So minus lambda t. So what we can then write, instead of having to go through all that trouble, is we can just write minus lambda 2, sorry, minus natural log of 2, I should say, times by 10, which is t, over the half-life of 87.7. And so now we've got everything filled in, so now we can just solve this by chucking it into our calculator and see what we get. And so when we compute that, well, we get a value of 8.316 times 10 to the 24. So that's the number of particles that will be remaining after 10 years have passed. So if we want to figure out the total energy released, we want to look at the difference in particles, since we know that for each particle it releases a discrete amount of energy. Okay, so to do that, all we need to do now is we need to look at, as I said, so the difference in the number of particles. So that's going to be equal to 9 times 10 to the 24 minus 8.316 times 10 to the 24. And so that gives us a value of 6.84 times by 10 to the 23. And so now, as I mentioned earlier, that's how many particles will be decaying. And we know from part A that when each particle decays, it releases 9.0 times 10 to the negative 13 joules of energy. So now we can say that the total energy released is going to be given by 6.84 times by 10 to the to the positive 23 times by our answer from part A, which was 9.0 times 10 to the negative 13. And that ends up giving us a final answer of 6.2 times 10 to the 11 joules. And there we go. So that is our final answer for the 2021 HSC Physics paper. So I hope you've enjoyed or found it useful and learnt something new, and hope you're feeling confident going into your own exams. So if you have enjoyed, please leave a like, subscribe, and comment if you'd like to see any future content similar to what we've done here today. And I appreciate it. Thanks for watching, and I'll see you next time.